Hi guys, my name's Ryan, and today I'll be talking about the algebra and dissection of types. So if you want to follow along, I posted the slides. Also, I just compiled them like 5 minutes ago, so hopefully everything works. But they're at that link up there. So let's get started. Let's get started with an overview of algebra. So we're all pretty familiar with the reals. You know, we've grown up using them. And oftentimes we've used plus, you know, when we're just trying to add two things, figure out how many things we have. But we can type plus, we can know what its type is, right? So what we think of as plus is really, it's you take one real, and then you take another real, and we return a third real. So what this means is that plus is an operator on the set of reals, and specifically it's a binary operator on the set that's closed. So what closed means is that it returns something that's still inside the set. This makes sense? And then we denote these kinds of algebras with this kind of notation, with the parentheses, with the left side being the set that we're interested in, and the right side being kind of the operation we're considering when we're going to be discussing different algebraic structures. So let's take, for example, kind of two algebraic structures that we know might have a similarity. So we're going to take the reals and addition, and then also bools and or. So we can say a few things about these. We know that both of them are closed. They return an element of the same set. What we also know is that the operators are associative. So if I do A, if I do B plus C and then plus A, it's really the same thing as A plus B plus C, right? I'm not doing anything really fancy here. It also works for OR as well. And then one final thing that they share in common is that there exists an element, which is called the identity element, inside the set, such that when you basically perform the binary operation with an element, the identity element, and a different element of the set, you always get back that element that's not the identity. So for addition, it's 0, right? So you just add 0 to whatever number you have. It's the same as really having done nothing. And for OR, it's false, right? So basically, if you have something or false, well, then it's just whatever the truth value of that other, the A is. So both of these actually are described by the same algebraic structure. They're described by monoids. So monoids are basically just sets with a binary operation that follow these 3 rules. So not too complicated. So now I'm going to go into a little bit of algebraic data structures. So in this talk, we're only going to be focusing on algebraic data types. And actually, specifically, we're going to restrict ourselves to regular data types, algebraic data types, for any of those who wanted to use nested types. And so generally, when we're making an algebraic data type, we can have one of 2 ways to kind of construct it. We can either kind of have a data constructor that has multiple inputs, or what we can do is we can have multiple data constructors, right? And so you can say, you can do something like double, where you just take something and you basically now have the product of that thing. Or you can have, say, the set of cards. And so the set of cards is denoted by a different data constructor for each type of card. So let's look at each of these cases in turn. So if we're going to define product, you can write it in Haskell. So I'm going to use mostly Haskell syntax for this because it's easiest, and also if we read the papers, they're also in Haskell. So we can define a product this way. Really what we're thinking about here is that it's the same thing as a tuple pair. And whenever I use that kind of equals with a squiggly on top, that means it's equal up to an isomorphism. So what does this mean? So when you have something that's equal up to an isomorphism, it means that there's a one-to-one projection between the two. So I can take any product, AB, and convert it into a pair using the standard tuple notation. And similarly, I can take any pair and produce a product set. They're one-to-one. So I'm going to write it like this. I'm going to write it infix. We'll see why later. But you can do this in Haskell as well with type operators. In this case, it's just a formatting of the way that Haskell works. And I'm usually going to try to describe the data constructors with a little hat on top of it, just in case it gets confusing. Whereas the type constructors themselves, which will just be the standard times here, is not that. So let's do a little neat trick. We can define the following data type. We can define a data type called 1, which only has one constructor. It only can construct 1, so that's the one with the hat on it. How many ways do you think there are to construct a data type that's basically the product or the pair of 1 and A? You guys have a guess? How many ways? Any guesses?
The size of A?
The size of A, right. So basically what we're dealing with here is that there's only one way to construct the one, and so it's a little bit redundant here. It's not very useful information. And so we can say that, well, we can write these kind of isomorphisms that basically one we think can hold in this relation, such that if I have a product of 1 and A is equivalent to the product of A and 1, there's an isomorphism between them. And similarly, it's all just equivalent to A, right? I can always construct an A in a pair as well, because I know that there's only one way to construct the one data type, which is with the one hat constructor. And so let's remember the monoid rules. So we remember that an operator returns an element of the same set. So here I'm saying that basically the product operator returns an element of, so it takes in, here I'm using the kind notation, but basically I'm saying it takes in a type, a Haskell type, and it takes in another Haskell type, and it returns to you a different Haskell type. So it's closed. The operator is associative. So what this means is that if I have the product of A with the product of B and C, it's the same as the product of A and B with C. And this is also pretty easy to see because we can easily just say, well, I need to have all three of them, and there's a pretty easy isomorphism between it, just whether or not you're putting it in kind of like the left slot or the right slot. And also there exists an identity element such that the relation holds that we've seen before, that basically the one doesn't provide a lot of information for us. And so what we find here, is that product, like when we think of product as a type, it actually forms a monoid, which is kind of convenient. So now let's look at sums. Oops, ignore the first line because I typed that incorrectly. So we're going to say sum is equivalent to basically the either. So we've seen either constructors. So either constructors are basically you have either a left or you have a right. And again, there's an isomorphism between sum and this Haskell notation. And what we're going to do is we're going to write it this way. Again, we're going to write an infix. We're going to say the type constructor plus, which takes in A and B, two types, can be constructed as either with the left data constructor and an A, or the right data constructor and a B, right? We can have one or the other, but not both when we're making values. So let's do another neat little trick. So here we're going to define a new data type, and the data type is called 0. And does anyone know why this data type is a little bit weird from the other ones?
How do you make it?
Right. Well, someone said it. How do you make it, right? I haven't given you any data constructors. There's no way to make this thing. And so if I want to make this function, this is perfectly valid Haskell, uncallable. I can make a function that goes from type 0 to A. I can just never ever call it, because I can never provide a value of type 0. So that means that I will never actually throw this error, this sad face error on the right-hand side, which is kind of convenient. I don't like errors. I don't like my program crashing. Also in this lecture series, we're going to just completely ignore bottoms. If anyone is, you just always do that. In which case, we can also think of this relation holding, kind of similar to what we had with the reals. If you have A plus 0, it's equivalent to 0 plus A, which is equivalent to A. And this is because if I have, say, the first one, an A plus a 0, well, I can never make the right data constructor. I can never pass a 0 value to the right data constructor. I can only pass the A to the left one. So remember, sum will also follow the monoid rules. We've just basically seen them. We know that it's closed. The sum takes in two different Haskell types and returns to another Haskell type. It's associative, so I can have either an A or a B and a C, or I can have A or B and C. They're equivalent up to isomorphism. And also there exists the identity element such that the 0 element, such that really you can't construct the data constructor. It's equivalent to just having the element, the type by itself. So we're also going to define two extra types. So we're going to define a constant. So normally this is defined, if you guys have read or saw there was a talk about basically deriving functors for free and a variety of other things. So that's using a pattern called polynomial functors. This is just a lower level than that. So we can construct a constant value, which has maybe some type, but there's only one data constructor. Because it's constant, you can't put anything in it. And then we're going to have the identity type, which is quite simple. It's just the identity of X is the identity of X. So we'll use that later, but I've just reminded it to you here. So now we're going to get a little bit more complicated. We're going to talk about semiring. And another name for a semiring is a rig, which is a joke. It's supposed to be a ring without the negation, or without the negative, because, you know, people who do algebra have really weird jokes. And so it's defined by the following rules. Basically, the additive operator and 0 forms a commutative monoid. And the commutative part means that we can switch the operator. We'll switch the two inputs to the operator, and it basically gives us the same thing. We have another monoid, which is the times and a 1 operator, and a 1 value. We say that times distributes over the addition operator. So really what we're saying here is that we're saying A times B plus C is equivalent to A times B plus A times C. So if I was thinking of this as a data type, I could say, well, I could have, say, a string and either like a int or a float, right? Well, that's really the same as saying I'll always have the string on the left-hand side, and then I'll have either a string and a integer or a string and a float, right? Those are the only two things I can really do. It's the same when again, this is another up to isomorphism.
Times doesn't have to be commutative?
No. In this case, it happens to be if you do up to isomorphism, but for the definition of semiring, it does not. And also, 0 is the annihilator for times. So this is kind of interesting. So if you have some data type A with the product of 0, it's really the equivalent of 0, right? Because how am I going to put into a pair the 0 value? I can't do that, right? It's just there are no 0 data constructors, and therefore I can't actually make it. So it's equivalent really to having the 0 data type. Everything make sense? Okay. So we know that ADTs, as we've defined them before, as we've kind of built them up from scratch, form a semiring. That's pretty awesome. So we have a way of describing the structure. There's also another type of very similarly related structure called a star or a closed semiring. So what a closed semiring is that it has this unary operator star, and it's defined recursively this way. So A star is equal to 1 plus A star, or 1 plus A star A. And so intuitively, if you expand this out, if you just keep substituting in the definition of A star into the right-hand side, what you get is 1 plus A squared plus A cubed plus A fourth, and keep going and going and going, right? And note that this doesn't work for all closed semirings, but in this case it works for us. So what does this look like? Well, what if we want to construct a list data type, right? What really is in the list data type? Well, we can have a list of 0 elements, or we can have a list of 1 element, or a list of 2 elements, or a list of 3 elements. It can go on forever, right? So star semirings basically provide us a way in which to encode a list if we want to inside Haskell, or for data types. So we know that ADTs can be described as a closed semiring. So now I'm going to make a quick detour into what a zipper is. How many people are familiar with zippers? Okay, a few of you? Okay, so this is just going to be very quick, and then the reason why is because it comes in good context later. So zippers are a convenient way of traversing a structure such that it keeps track of where you are. So zippers are also sometimes known as what is called a one-hole context, which is basically just, if you have a data structure, you can punch a hole in it, and that's kind of, it marks where you are. That's usually what people think of it as. So if we have, say, our list data type, the way in which you can have a hole in the list is basically you have some element in the list is your hole, and then you have things to the left of your hole and things to the right of your hole, right? And then, so that's described as a zipper is basically a pair of lists. So the first list will be basically everything before your hole, and the second list, because this is not defined, will be everything after the hole. Such that you know where you are. Currently, you are at the head of the second list while you're traversing it. That's usually how this is defined. There are other ways to define zippers, but they're all equivalent. So zippers are great because they allow you to do constant time local updates to a data structure. If you, for example, were taking a list and you kept accessing the 5th element of that list, and say there are more than 5 elements, and you just keep updating it. Well, you're always going to have to do O of 5 to go get there. Or if it was at the end of the list, oh man, that sucks. Or O of n to update that last element every time. But if you make a zipper and you know you're going to be at the end, you can basically just pop your hole down there at the end. So you can move a zipper left and right. You can change where the hole is. And then you just keep updating that value. And now it's a constant time algorithm. And zippers are actually used extensively in Xmonad. For any of you who are familiar with that, they use it for basically figuring out the layers of windows and stuff like that. So now let's jump into derivatives. So we can think of the derivative of a type as actually, it calculates for us the one whole context. And we can think of it as giving us kind of where we are within the data structure. It's the same as the zipper, but in this case, the derivative will allow us to calculate it for any type, or any regular algebraic data type. So we're going to go to calculus and just kind of remember our laws for derivatives. So if you have the derivative of a constant, it's equal to 0, right? So similarly, if I say took a value of type k, so k is a constant, right? What's the context for that? Well, that doesn't really make sense. We're not talking, it's the only thing in context at the moment, so there's not more context to the value that you have. So we can see that this would, basically if we took the derivative of something like nil, we'll get something that would be like 0 if we did have a value of type 0. But in this case, not possible. So the derivative of a variable by itself is 1, so if you have like the derivative of x is 1. So here we represented basically that kind of concept with the identity type. And so the derivative of the identity is 1. So really, what does this look like? So what this says is that, so say I have an int, right? Well, the only context is that int. Or, sorry, I shouldn't say int because int is a constant. So say just, right? There's only, say I had a JV with only a just constructor, something like that. Then the only context is that value that's inside it. There's no other types of context. So there's only one place for the whole to get. So there's also a derivative for products, and it follows just the general product rule, or more generally, it's Leibniz rule. So basically, it's just the derivative, when you take the derivative of a product, it's the derivative of the first one with the product of the second guy, plus the first element and with the derivative of the second. So what does this look like? So let's take an algebraic form where we have a product of two values, x and x. So if we take the derivative of that, what we'll get is basically something of this type. We'll have either a hole in the left-hand side, or we'll have a hole in the right-hand side, which is what we've encoded here. So the values can either be, we're on the left, we have a hole in the left, and we haven't yet processed the guy on the right, or we've already processed the guy in the left, and we're going to be processing the guy on the right. Okay, and so then you can also do the derivative of a sum. So the derivative of the sum is pretty easy. It's just the derivative of both things added together. So, for example, if you took the algebraic form x plus 1, well, then really the only place you can have a context is within that x. So if we think of the maybe constructor, if you have a value of that type, you can either have nil, but there's no context to nil, it's just a constant, or you can have just an x, in which case the only way you can really think about your context is that you must be in the just, right? That's the only place you can be. That's the only place where there's a hole. So now I'm going to move on to dissection. So dissection is really just a generalization of derivatives. And for this, I'm really going to just kind of gloss over some of the mathematics behind this because it requires some linear algebra and a little bit more kind of what's called a semiring homomorphism. So you basically project the semiring of types into the semiring of regular expressions, and then you can use that to basically calculate dissections. But we're just going to show you what it looks like. So when we calculate the derivative of a type, we don't really differentiate between whether or not we have things to our left that we've seen before. Because, like, say I start off with a list, and I put a hole in the start. Well, if I keep moving right, I've already seen all the elements that I passed by on the left, right? So take, for example, I'll just tell you this is true. So the derivative of a list is basically a pair of lists, right? That's the zipper. So that tells us that the things we've already traversed and the kind of hole, and then the thing afterwards. But for dissection, what we actually do is that we denote those things that have already been processed differently from those that have been yet to be seen. So this is mostly from a paper. The original paper on this was called Clowns to the Left, Jokers to the Right. So sometimes people will call the things that have already been seen clowns and things that haven't been seen yet jokers, which is it's based on a song that I don't know. And so dissection follows the similar rules as we have for derivatives. So the dissection of a constant is 0. The dissection of an identity is just 1, right? There's no, like, I'm not labeling anything. Again, I only have one hole or one place to put a hole. The dissection of a sum is just the sum of the dissections. And the dissection of the product is a little bit different, right? So the dissection of the product is I'm going to dissect the left one, and then I have this little funny operator here, which is kind of like half of the dissection symbol. And then, or I can do basically that funny symbol on the left-hand side, and, or like added with the, times with the dissection of Q. So what is that little funny symbol? So basically what the symbol equates to, or intuitively that you can think of it, is that the left clowns, these are called, it's clowns, takes your data type and it marks it. It labels it as the things you've already seen. And then the right one, which is called Joker often, labels basically all the types that you've yet to see. So, for example, we have the derivative of a list, gives us a pair of lists, but in this case, the dissection of a list is a little bit different. What it gives us is that it gives us a pair of lists, but where it's labeled. We know that the left list is labeled with this kind of, you can just add it as a, like a phantom type or whatever onto your, in Haskell, such that the things on the left are now not just, they've been marked as being processed. The things on the right have been marked as being not processed. Whereas before it was just kind of like random convention. And then note that basically dissection is it's actually it's equivalent or it's similar to divided differences, but it provides a generalization of derivatives because what happens if I actually use the same label function? Well, then I just get back to the derivative, right? Because now I'm not distinguishing between the two labels. Now I can build an isomorphism with my original zipper type. Right? So kind of what have we learned today? So what we've learned about is kind of how to describe an algebraic structure and a little bit about monoids, because monoids are helpful for describing, well, a bunch of structures, but products and sums. We've described how addition and times, or the sum and the product, each form monoids, and which together form a closed semiring, which remember also has that unary operator, the star. We've kind of learned a little bit about how to take the derivative of a type, which gives us one whole context. And also we've learned its extension, the dissection of a type, giving a one whole context that is actually parameterized with a label of what you've seen before. And that's it. Any questions? No questions? Yeah.
How do you encode partial derivatives? Is it over multiple types?
Yeah, so partial derivatives are a little bit more complicated. That's kind of what dissection will kind of do that for you, because you're basically labeling one or the other, but I don't know precisely how to do it generically. So there's a way to do this generically that I haven't actually described. But any other questions? Yeah?
Can you point to any literature about what you just did?
Yeah, so this is based off a few papers. So one of the papers that you'll probably want to read is data types a la carte, because that's required basically for the main paper about this topic, which is Clowns to the Left, Jokers to the Right by Connor McBride. And then afterwards, there's basically a paper that describes how to generalize or how to do these dissections. Because the problem with these derivative rules is that, and the reason why I just told you what the derivative of a list was, is because if you try to calculate it normally, you basically have to define a list through subtraction. And subtraction, and rationals. And subtraction of rationals of types doesn't make sense often. I mean, you can define what a rational of a type is and what the subtraction of two types are, but in general, it's not defined. So there's a third paper that basically talks about, I forget exactly, it's like pattern functors over regular expressions or something like that, but basically talks about how you can project this system of this semiring into another semiring, which is the regular expressions, which can then be expressed as which can then be defined as a deterministic finite composite. So I can get you that paper. I just haven't added the references yet. Yeah.
Is that because derivatives don't have recursive data types?
For the subtraction or what?
You can't really do lists with what you told us about derivatives because you didn't do recursive.
Yeah, so the way you can do lists, so I didn't really tell you, but you can redefine. So another way to think of that star operator is 1 over 1 minus a. But that doesn't make sense, right? That doesn't make sense in types. But if you take the derivative of that, what it gives you is 1 over 1 minus a squared, right? So if you factor that out, that's 2 lists. So you can think of it that way, but I don't really like using the subtraction and the rationalization, or the rational types, because basically you have to project sort of a ring, do the calculation in the ring, and then project back to the semiring, which is, of course, partial. So there's a way to do it without doing the subtraction that requires deterministic finite automaton. Oh yeah, sorry.
Can you, this is probably a big question, but can you explain what a whole with context is?
Wait, sorry. So, repeat the question.
Can you explain what a whole with context?
So the whole just kind of marks where you are. So a lot of times actually when you use zipper, what you'll see instead is so there's several ways to define it, but what the whole will be is that it will be a distinguished element. So another way to define a zipper is like you would have everything, the list of everything to the left, and then you would also have a product of the current element that you were looking at, that would be the whole, and everything that you haven't seen before. So the whole is basically just a marker of where you are. It's a convenient way of doing traversals, or traversals where you're constantly located. There's one also thing that's kind of cute about this is that you can do, so if you think of this as like divided differences, you can also do kind of this for derivative, you can do like a second derivative. And what that gives you is that gives you two holes, where everything on the first side, everything on the very left, is basically things you process with two different types of algorithms. Everything in the middle is one where you process it with one routine but not another. And everything on the right is basically something that you process, or sorry, the other way around. But everything that you process with both routines. So because you have now three labels that you can mark down, kind of like where two things are. So you can kind of mark have two like co-recursive or like co-routines. You can kind of mark where they are in the list, or where they are in whatever structure. Oh yeah, you can do this for like trees or all sorts of stuff.
Some folks might find it helpful to think of the whole as being a cursor.
Yeah, that's great. So the whole is also defined as a cursor. That's a very good way of building it. Any other questions?